So let's get started. All right. Ballistics, guys, can be broadly divided into three primary categories: internal ballistics, external ballistics, and terminal ballistics. Each category provides vital insights into different stages of the projectile's journey. So today, we will begin by focusing on internal ballistics and gradually explore the remaining aspects of this field. So as you can see in slide 2, okay. Before we dive deeper into the internal ballistics, I want you to know that there is three types of ballistics. Just a second, guys. All right. So we have three types of ballistics. We have the internal ballistics. So this area focuses on the processes occurring inside the firearm from the moment the trigger is pulled until the projectile exits the barrel. The terminal ballistics, this pertains to basically the effects a projectile has once it strikes a target, such as a body or a certain surfaces, and it plays a crucial role and a critical role in understanding the injuries caused by gunshot wounds. We have the external ballistics. So this examines the projectile's flight after leaving the barrel, studying its trajectory and the influences of gravity and atmospheric conditions. We have also the wound ballistics. This area, guys, a specialized subfield that studies the injury patterns caused by projectiles, helping us understanding the severity and type of wound inflicted. So each of these areas plays a significant role in the investigation and analysis of firearms, which is related to incidents. Today, we will delve into the intricacies of internal ballistics, beginning with the movement of a projectile within the firearm. So, as you can see in slide number 3, we have the case, which is composed from the bullet, the case, the powder, the primer, and we have the GSR inside the case. So I want you to know that internal ballistics refers to the processes occurring inside the firearm. As the projectile is fired, these sequences begins with the ignition of the propellant and continues until the projectile exits the muzzle. So by understanding internal ballistics, scientist or forensic scientist helps determine the force exerted on the projectile, the factor that influence its motion, and the relationship between the firearm's design and projectile performance. So the internal ballistics, as we said, process includes the ignition of the propellant, the buildup of pressure, and the movement of a projectile down the barrel. This phase is essential for understanding how the projectile is propelled and how this affects its trajectory once it leaves the firearm. So to further understand internal ballistics, guys, we need to familiarize ourselves with a few key terms. There are two primary types of barrel designs, and please have an attention here. We have the smooth bore and we have the rifled barrels. The smooth bore firearms like shotguns feature smooth barrels, and they typically fires spherical projectiles such as slugs or pellets. These projectiles do not spin, all right? So these projectiles do not spin, resulting in a less accurate, more spread out trajectory. However, the rifled barrels, so these firearms have grooved barrels that impact a spin on the projectile, stabilizing its flight and making it more accurate. So basically, this design allows for greater control over the projectile's trajectory, which is essential for precision shooting. The design of barrel, whether smooth bore or rifled, affects how the projectiles behave inside the firearm and impacts its performance once it's discharged. So, as you can see, and moving forward to slide number 4, okay. Now we will examine, guys, the 3 primary phases of internal ballistics. When it comes to internal ballistics, we have 3 phases. We have the lock time, we have the ignition time, and we have the barrel time. So when talking about lock time, this refers to the time it takes between the release of the sear and the striker's impact on the primer. A shorter lock time is desirable for rapid fire, and it can take precisely measured using the motion sensors. When talking about ignition time, the time taken for the firing pin to strike the primer and ignite the propellant. This phase typically lasts only about very few seconds, around 0.002 seconds. So it's too fast. Now talking about the barrel time, this is the time taken from when the trigger is pulled to when the projectile exits the muzzle. The combined total of lock, ignition, and barrel time generally ranges between 0.003 and 0.007 seconds. And this is very accurate here, guys. So each of these phases plays a role in determining the projectile's speed and accuracy, and they are critical in forensic analysis for determining factors such as the muzzle velocity and trajectory. Now, we're going to talk about the phenomenon of internal ballistics. So what will happen inside the gun? We will have a closer look at the ignition and combustion processes that drive the projectile forward in a firearm, which are fundamental here to internal ballistics. These processes, guys, are the foundation of how a bullet is propelled out of the barrel, and understanding them is very crucial for both forensic analysis and firearm design. Let's have a look on the role of the primer. Everything begins here with the primer, which is an essential component of a firearm cartridge. So when the trigger of a firearm is pulled, the firing pin strikes the primer at the base of the cartridge. And then the primer consists of a small sensitive compound that, when struck, generates a spark. And the primer's function here is to ignite the propellant inside the cartridge casing. It's important to note that this ignition process is incredibly fast and involves a high amount of heat and pressure being released from a very, very small area. So this rapid release, guys, of energy From the primer begins the combustion process, and once it's ignited, the flame spreads into the propellant, creating a significant reaction. Now, what about ignition of the propellant? Once the primer is struck, it ignites the propellant, typically smokeless gunpowder or a similar substance in modern ammunition. So here, the propellant is a chemical, guys, is a chemical compound made of a mixture of materials that burn in a controlled but rapid manner. At the point of ignition, it's really important to know that the propellant starts to undergo a chemical reaction. A process of exothermic combustion is this chemical reaction. This means that the reaction not only produces heat, but also rapidly releases gas in the form of hot, expanding gases. So the heat generated by the combustion of the propellant is intense, often reaching several thousand degrees Fahrenheit. So this temperature is too high and is high enough to turn the solid propellant into a gas almost instantaneously. So the creation of these gases is where a large portion of the energy from the combustion process is stored. The volume here of these gases increases rapidly as the propellant burns, creating a significant increase in pressure within the cartridge casing, of course. So this pressure, guys, is really essential for the next step, which is the propulsion of the projectile. Now, what about the expansion of gases and increasing pressure? The factor, guys, or the key factor here that dives the projectile out of the barrel is the pressure generated by the rapidly expanding gases. As the propellant burns and turns into gas, it creates a highly pressurized environment within the cartridge casing. So this is really important here because this pressure forces the projectile, known by the bullet, which is the bullet, to move forward inside the barrel. So the efficiency of this gas expansion is determined by the properties of the propellant and the volume, of course, available for the gases to expand. In a typical firearm, guys, the chamber is designed to contain the gases as the propellant burns. And as the projectile begins to move down the barrel, of course, the gases continue to expand behind it, pushing it forward at a very high speed. So the rate of combustion here and gas expansion is very crucial in determining the velocity of the projectile. So the more rapidly the gas expands, the faster the projectile will move. And additionally, the length of the barrel affects how long the gases can continue to accelerate the projectile. So a longer barrel provides a longer time for the expanding gases to push against the projectile, which lead to a higher velocity when the bullet exits the barrel. Now, when talking about factors affecting combustion and pressure, it's really important to know that the ignition and combustion processes aren't solely determined by the physical properties of the primer and the propellant inside it. So several factors influence how efficiently the propellant burns and how much pressure is generated. So one of the most thing is the type of propellant. So here, different gunpowders or other propellants burn at different rates. Some propellants are designed to burn steadily generating a consistent amount of pressure over a longer period. Others may burn more explosively here, releasing energy very quickly. For example, if you have a ball powders, these ball powders are spherical and burn at a relatively constant rate, while stick powders are cylindrical and often burn faster. So this creating higher peak pressures quickly. Another thing uh, that affect the combustion and pressure is the burn rate. The burn rate here, guys, of the propellant is a critical factor in internal ballistics because simply a slow burning propellant, for example, will generate lower pressure over a longer period, resulting in a slower but more controlled acceleration of the projectile. In contrast, a fast-burning propellant generates a higher peak pressure in a shorter time, which leads to a rapid acceleration of the projectile. Now, a third thing that also affects the combustion and pressure is the environmental factors. So, external factors such as temperature, humidity, attitude can significantly affect how efficiently the propellant burns. So, cold temperatures here may slow the rate of combustion, leading to lower pressure and velocity, while a high temperature can speed up the combustion process, causing the gases to expand more quickly and increase pressure. So, also similarly, humidity can alter the moisture content in the propellant, which could impact its burn rate. Now, also, we have the barrel length and design also affect the combustion and the pressure. So here, guys, the length of the barrel and the type of rifling, the spiral grooves, for example, inside the barrel, also play a key role. So if we have a longer barrel, this allows the gases to act on the projectile for a longer time, typically resulting in higher muzzle velocity. Rifling inside the barrel causes the projectile to spin, which stabilizes its trajectory. While rifling doesn't directly impact the combustion process, it does influence how the gas pressure interacts with the projectile and helps maintaining accuracy. Now we have also the chamber size, of course, and the cartridge design also affect the combustion and the pressure. So here, guys, the size of the chamber and the cartridge casing also play significant roles in the combustion process. So a larger chamber allows more room for the expanding gases, while a smaller chamber increases the pressure more rapidly. Talking about the cartridge casing, also must be strong enough to contain the pressure generated by the combustion of the propellant. So, a well designed casing will prevent ruptures or failures, ensuring that efficiencies in the combustion process can result in unspent propellant, excessive heat, or dangerous levels of pressure, potentially compromising the firearm's performance or even causing a malfunction. So, in forensic science, understanding the efficiency of combustion can help determine how a firearm operates, and how a projectile was propelled. So, sorry. Can you hear me? Am I audible? So I was saying, in forensic science, understanding the efficiency of combustion can help determine how a firearm operates and how a projectile was propelled, and the possible cause of any malfunctions in such case. So it also aids in analyzing the conditions under which the firearm was used, such as temperature or improper ammunition. So now we're going to talk about transition to barrel time, which is very important here. As the projectile is pushed down the barrel, it accelerates rapidly and the gases continue to exert pressure on it. So the duration for which the projectile remains in the barrel, known as barrel time, is typically very brief. So barrel time is generally in the range of 0.003 to 0.007 seconds, which is extremely fast. And this is very accurate here, guys. So the high pressure and speed at which the projectile travels down the barrel determine how efficiently the energy from the combustion is used. Once the projectile exits the barrel, the combustion process is complete and the projectile enters the phase of external ballistics. However, the precise dynamics of ignition, combustion, and the resultant acceleration within the barrel have already determined the velocity, energy, and trajectory of the projectile, all of which are critical for understanding how the firearm discharged the bullet. Now, moving forward to slide number 6, we're going to talk about terminal ballistics. So once the projectile, guys, exits the firearm, it enters the realm of terminal ballistics, which is the study of what happens when the projectile impacts the target. So terminal ballistics is primarily concerned with the energy transfer from the projectile to the target, including how the projectile damages tissues, bones, or other materials like surfaces. So there are several factors that influence terminal ballistics. We have the projectile design and the distance. Talking about the projectile design, the shape and material of the projectile play a significant role in how it impacts the target. For example, hollow point bullets are designed to expand upon impact, creating a larger wound and transferring more energy to the target. On the other hand, full metal jacket bullets are designed to penetrate deeply, causing less damage upon impact, but potentially leading to more severe tissue damage deeper inside the body. Now, let's talk about the distance. The distance from the shooter to the target also affect the impact. So shots fired at close range may cause different types of wounds comparing to those fired from a greater distance. So by examining the wound, and this is what I want you to know, by examining the wound caused by the projectile, forensic experts can often determine the type of ammunition used, the velocity of the projectile, and sometimes even the distance from which the shot was fired. And we're going to calculate how we can know the angle of impact, and we will see it in further slides. Now we're going to talk about slide 7. Okay. Are you still able to see the slides? Can you hear me?
Yes, ma'am, we can hear you. The slide is also visible.
All right. So now we're going to talk about the typical categories of muzzle range.
Just
Please
a
turn
second.
off
I'm
your.
sorry to interrupt you. I would just like to say one line that, dear participants, you are encouraged whenever ma'am asks a question, please unmute yourself and reply instead of writing it in the chat box. Because when ma'am is presenting, it is not possible for her to just go and watch what messages are coming in the text box. Okay, so please pay attention from the next time. Yeah, ma'am, you may continue now. Thank you.
Thank you. All right. So now we're going to talk about the typical categories of muzzle ranges. So the muzzle range refers to the distance from which a firearm was discharged. In forensic investigations, understanding the muzzle range is very critical for determining the circumstances of the shooting. So the general categories of muzzle range are hard contact, loose contact, near contact, intermediate range, and or indeterminate range. We're going to talk each of these ranges. Talking about the hard contact, as you can see in the slide, the muzzle here is pressed directly against the skin. So this creates a very distinctive wound, often with searing around the edges and a burn mark due to the hot gases existing the muzzle. And you can easily see the muzzle imprint in a hard contact range. Now, the loose contact, here the muzzle is very close to the skin, but not in direct contact. There may be some evidence of soot or burns around the wound, but the effects are less pronounced than in hard contact shots. Now, we're going to talk about near contact. Again, as you can see, the firearm is within about 5 inches of the target. So wounds from near contact shots may still have evidence of powder residue or seared tissue, but they are generally less intense than those from hard or loose contact. Now, talking about intermediate range, this range typically refers to distance between 5 and 40 inches here. At this distance, the shot may still leave a characteristic wound, but there will generally be no burn marks or even powder residue around the entrance wound. And finally, we have the indeterminate range. When there are no clear signs of soot or burns here, the range, guys, is considered like indeterminate. This usually occurs in longer range shots where the projectile has traveled a greater distance before even impacting the target. Okay, so when we have a greater distance, it's possible to say that it's an indeterminate range. Okay, so each of these categories helps forensic experts to narrow down the circumstances of the shooting and provides valuable evidence for crime scene reconstruction. Now, moving forward, we're going to talk about, the bullet injuries. And this is very important in forensic ballistics, guys. The bullet injuries can be classified into several types based on the path the projectile takes through the body. So it's really important to take into consideration the path of the projectile. So when talking about penetrating injuries, in such case, the projectile enters the body but does not exist. Okay? So basically, the projectile enters the body, penetrates the body, but it sticks inside the body. It does not exit. These injuries may cause significant internal damage depending on the projectile's design and velocity. However, the perforating injuries, in such case, the projectile passes completely through the body, creating both an entry and exit wound. So these injuries here tend to cause more damage over a larger area than penetrating wounds. Now, talking about tangential injuries, and this is very crucial here. As you see in the image, the projectile grazes the body without even entering it. So often it leaves a superficial injury on the surface without even entering the body. However, grazing injuries, these are minor, shallow abrasions caused by a projectile that travels very close to the body, creating a small wound. Okay? Now, understanding these injuries helps forensic scientists determine the type of projectile used, its velocity, and its trajectory, so all of which are crucial for crime scene analysis. Now, we're going to talk about external ballistics. So as you can see in slide number 9, external ballistics, guys, means the study of bullet behavior after it exits the firearm. So here we examine defects created by the bullet in the surrounding environment. So these defects can be categorized in several ways based on their interaction with the surface they strike. So the most common categories include penetrating defect, perforating defect, ricochet or deflection defect, and tangential defects. When talking about penetrating defect, I want you to know that this occurs when a bullet enters a surface but does not exist, leaving only an entry hole. This type of defect is typically observed in soft materials such as wood or drywall, where the bullet may lodge inside. However, perforating defect, in contrast, a perforating defect happens when the bullet enters and exits the surface, leaving both an entry and exit hole. This is often seen with harder materials like metal or even glass. Now, talking about ricochet or deflection, here the bullet, guys, strikes a surface but deflects off it an angle without fully penetrating. So it barely touches the surface. The ricochet angle and the trajectory depend on the nature of the surface and the bullet's energy. And this is a bit different from the tangential defect because tangential defect occurs when the bullet skims the surface at a shallow angle, which create a series of marks or scuffing. So the marks are often elongated and streaked in the direction of the bullet's travel. Now we're going to dive more into the angle of impact caused by the bullet defect. So as you can see in slide number 10, now I have a question. Does any one of you know how to calculate the angle I of impact in order to know, for example, the angle that the bullet enters a surface, or does
Ma'am,
anyone know how to calculate the angle of impact?
what is the formula for angle of impact?
Can you repeat, please?
Is
Ma'am,
it
there is
sin equal like
n
sin
equals to length of the blood stain upon width of the blood stain.
Sorry, I'm not able to hear you.
ma'am? Is it like sin I equals minor axis by major axis?
Absolutely. How did you know the major axis? How did you calculate the major axis?
Like the one that is wider and longer.
Yes, but how did you calculate it? How did you know that the
I
major
have
axis is the one?
diameter.
All right. Okay, let me explain. Can you see the pointer?
Yes, ma'am, it is visible.
All right. So this is the eye angle. The eye angle here, guys, is equal to this angle here. Okay. Okay, I will draw something. Wait. Hopefully, I would be able to draw. Okay. Okay. So let's say this is A. This is B. Okay, sorry, and this is C. I want you to know that I is equal to this angle. Okay? Do you know why? Can someone explain why? Because these angles, guys, are correspondent. Okay? So when calculating AB, AB is equal to EF, which is the caliber of the bullet. Now, because this is a rectangle, all right? So EF is equal to AB. But the question here, how EF, how we can measure EF? Simply, EF is equal to this line here. I will change the color. Okay. Which is the major axis. Okay, so if we want to calculate the angle of impact, sine I is equal to BC over this line. Let's say it's MN. Okay, and by doing so, we will be able to calculate the sine I. Now, I is the sine to the power -1, which is the inverse sine of the minor over the major. Okay, so as you can see here in slide 11, sine I is AB over BC, but the inverse sine is the angle I. Okay, and this is how we are able to calculate the angle of impact. Now, moving forward, we're going to... Yes?
Hello? Ma'am, can you please repeat this once again?
Of course, I will repeat. So let's erase everything and I will repeat it from the beginning. Okay. I was saying that this angle I is equal to this angle. Why? Because these angles are complementary. Okay, this is math. So how we can calculate the angle I? There is a formula that says that sine I is the minor, okay, over, sorry, the major over the minor. So when we calculate sine I, okay, this is too hard. Wait, I can do something. Okay, so sine I cannot even write. It's fine. Sine I, okay, look here, is AB over BC. AB over BC. This is math, okay? So how we found AB? Simply AB is equal to the caliber of the bullet, okay? And at the same time, AB is equal to the minor axis. If you look here, okay, AB is equal to the minor axis. Okay? So when calculating sin I, it became that sin I is equal to AB over BC. AB is the minor axis. BC is the major axis. So sin I became the minor axis over the major axis. This is sin I. Now how to calculate I? Simply, I is equal to the inverse sine. Okay? I'm sorry for the drawing, but we do not have other option. So sine to the power -1 of the minor over the major. Okay? Clear?
Yes, ma'am. Thank you.
You're so welcome. Okay. So now we're going to talk about something very important, which is the direction of travel of the projectile. How we can determine the direction of travel of the projectile. Simply, guys, if you have a look on the photo, it's really important to understand the direction of the bullet's travel after it strikes a surface, which is critical in crime scene investigation. So two main phenomena are used to track the bullet path. The first is called pinch point, and we're going to talk more about it. And the second is called the wake effect. The pinch point, as you can see, happens when a bullet strikes a painted surface. It often creates a small piece of paint, and that remains attached at the point of impact, which form what we call a pinch point. Okay? So this paint fragment can help identifying the direction in which the bullet was traveling when it impacted the surface. So simply, whenever you see this pinch point, okay, let's draw again. Whenever you see this shape, this is the pinch point. So the pinch point helps us determining the direction of travel of the projectile. So it's simply in this direction. Okay? Now, the wake effect is similar to the pinch point, but the wake effect here, guys, happens when the bullet interacts with metal surfaces, okay? The pinch point interacts with paint surfaces. However, the wake effect interacts with metal surfaces. It creates microfractures around the impact site, which arc in the opposite direction of the bullet's travel. So this can provide further insight into the bullet trajectories. So as we said, this is the wake effect, guys, as you can see here. For the drawing. Okay, so also the wake effect help us in determining the direction of travel of the projectile. Is it clear? Am I audible?
Yes, ma'am. Yes.
All right, great. Now we're going to talk more about the entry and exit of a bullet defect in windshield glass. So here it's more like challenging to determine the entry and exit point. Simply, windshield glass often exhibits distinctive patterns. So when impacted by a bullet. So these patterns are crucial in reconstructing shootings, especially when dealing with vehicles. Both the entry and exit point in the glass display a coning effect, which is a phenomenon where the glass deforms at the point of impact. So the entry side of the glass often shows a less pronounced coning effect, with the exit side, it's characterized by a more evident destruction. So this is due to the bullet energy, guys. So because of the bullet energy wave forcing particles outwards, This creates a more pronounced crater-like effect on the far side. So these defects often valuable insights into the angle and direction of the bullet travel, which provide essential clues for forensic experts. So as you can see, guys, the coning effect is this one. I will draw again. Okay, so this is the coning effect. Sorry. Here. This is the coning effect. Okay. The question is, which one is the exit effect, A or B? What do you think? If you look at these two photos, guys, which one is the exit effect? And why? Please take a moment and look at these two photos. What do you think? Which one has a larger coning effect? Open your mic and answer. I cannot see the chat box.
A is entry and B would be exit.
Absolutely correct. Bravo. So B is the exit defect because the coning is bigger in B. So whenever you have a bigger coning effect, this determines the exit point. Thank you. Now, moving forward, we're going to talk about something very important in forensic ballistics, which is the GSR and how forensic investigators are able to collect GSR and even analyze it. So if you look at slide, I don't know the number. Okay, at slide 14, gunshot residue, guys, analysis plays a crucial role in forensic investigations. So after a firearm is discharged, particles from the primer and propellants are released into the air. These particles travel towards the shooter and they can be deposited on the victim, the shooter clothing, or even the surrounding environment. The most common elements detected in GSR are lead, barium, and antimony. These elements originate primarily from the primer of the cartridge. Additionally, brass, which is the copper and zinc, used in cartridge case can also be detected during analysis. So the presence of these particles is often used to determine if a person has discharged a firearm. Now, talking about the methods of analyzing GSR, we have so many methods and we're going to illustrate each of them. We're going to talk about the NAA, which is the neutron activation analysis. The neutron activation analysis, guys, can detect barium and antimony. But the problem here is that the neutron activation analysis is very costly and expensive and requires access to a nuclear reactor. Okay? However, talking about the FAAS, which is the Flame Atomic Absorption Spectroscopy, has largely replaced the neutron activation analysis. Why? Simply due to its lower cost and better efficiency. And we have also the grease test. It's commonly used to detect nitrates, which is a component of unburned gunpowder. So this test is often employed to confirm the presence of GSR on a shooter's hand. However, it's really important to remember that negative results in GSR testing can occur due to several factors, guys, such as washing hands, wearing gloves, or even using lead-free ammunition. So now we're going to dive more about the analysis of the GSR. Okay, are you still able to see the slide number 16
Yes.
and 15? Perfect. This is very important here, guys, because gunshot residue analysis involves the detection and identification of microscopic particles which are left behind when a firearm is discharged. These residues include both organic and inorganic particles. The inorganic particles, specifically those containing lead, barium, and antimony, serve as primary indicators of firearm discharge. So several techniques are used for GSR analysis. We have the colorimetric test. So these early methods, So these early methods were used, but are less reliable due to contamination from the environment. We have the neutron activation analysis as detects antimony and barium, but requires a nuclear reactor, as we mentioned that before. We have the atomic absorption spectroscopy, which is the AAS. It detects lead, barium, and antimony in trace amounts. We have the scanning electron microscopy, and this is the best one, known by SEM. So SEM, guys, is the gold standard for GSR analysis. Why? Simply due to its high resolution, which allows forensic experts to examine the unique characteristics of GSR particles at the nanoscale. It also incorporates energy dispersive X-ray spectroscopy, known by EDS. I don't know if you heard about it. The EDS enable elemental analysis of the particles. So we're going to illustrate the SEM and EDS deeply. SEM's high resolution and non-destructive nature make it an invaluable tool for investigating gun-related crimes because it allows for precision and precise identification and analysis of GSR, which ensure accurate results. So, when a firearm is used, guys, it releases microscopic particles into the air, which then settle on surrounding surfaces, including the shooter's hands. So these particles can be traced back to the discharge, providing vital information in forensic investigations. Because GSR analysis not only helps in confirming whether a firearm has been used, but it also offers invaluable insights into the nature of the shooting event itself. So the residue that we analyze in GSR can be categorized into two broad components, as we said before, the organic and the inorganic component. The organic components, again, typically come from the propellant and lubricants used in firearms, while the inorganic components originate from the primer, the casing, barrel, and other part of the weapon. So the inorganic particles, guys, that are particularly useful in identifying gunshot residue are those containing lead, barium, and antimony. So these elements come primarily from the primer, which is the small but powerful explosive charge that ignites the propellant. For years, lead has been a key indicator in GSR analysis, but it's important to note that an environmental concerns has risen. Lead-free primers are becoming more common in firearms. So this shift has made it necessary for forensic scientists in order to adapt their methods of analysis. The primary ingredients are central to the detection of GSR because they are the source of particles that contains elements like barium, lead, and antimony. So the primary explosive compound is often lead stephate, while the oxidation and reduction products include barium nitrate and antimony sulfate. So together, these compounds form the foundation of the evidence we look for during a GSR investigation. Now, why is GSR analysis so significant, guys? First and foremost, detecting these microscopic residues serve as a confirmation that a firearm has indeed been discharged. However, the role of GSR analysis extends far beyond simple validation. By studying the distribution pattern of these residues, again, the lead, barium, and antimony, forensic experts can infer critical information such as the number of shots fired, the proximity between the firearm and its target, and potentially even the direction of fire. So this ability to deduce such intricate details is really essential in linking individuals or objects to action involving firearms because it aids in identifying perpetrators, even reconstructing crime scenes, and corroborating or challenging witness testimony. So the value of this information in criminal investigations cannot be observed and cannot be overstated. So we said before that we have several techniques that are used for GSR analysis, like the AAS, the NAA, and the SEM. So among these techniques, scanning electron microscopy, which is the SEM, has emerged as the superior method for GSR analysis. SEM stands out due to its high resolution, again, and its ability to perform microanalysis at the nanoscale level, guys. So this makes it possible to visually examine and accurately characterize GSR particles because it identifies their unique morphological features. So this level of resolution allows forensic scientists to confidentially distinguish between gunshot residue and other similar substances, reducing the risk of false positives. So, moreover, SEM can be coupled with energy dispersive X-ray spectroscopy, known by EDS. EDS, guys, enables elemental analysis of the particles. So this combination ensures that GSR particles are not only visually identified, but also chemically confirmed, further strengthening the reliability of the findings. So perhaps most importantly, SEM is non-destructive technique. This means that evidence can be retained for further analysis if necessary, ensuring that the integrity of the sample is preserved. Furthermore, the development of automated SEM has reduced the need for highly specialized personnel, making the technology more accessible and efficient. Now, in forensic science, guys, maintaining consistency and accuracy is paramount because SEMs are particularly valuable because they allow investigators to analyze the microscale structures of particles, revealing the unique fast cooling droplets of molten material that are characteristic of GSR. So when paired with EDS, SEM provides a comprehensive solution for both visual and compositional analysis, which offer a clear and unambiguous identification of GSR particles from the trace samples. For standardization, ASTM International, a globally recognized organization, has defined specific technical standards that govern GSR testing protocols. So one such standard is ASTM E1588. For those working in the forensic ballistic field, you should be familiar with this software. So ASTM E1588 sets guidelines for performing GSR analysis using SEM and EDS. So according to this standard, SEM is combination with EDS must be performed through automated software to ensure a consistent and repeatable workflow. So automation eliminates here user bias and produces actionable data in the form of standardized reports. So once the automated screening process is complete, manual confirmatory analysis is necessary to verify that the particles are indeed GSR. So collecting sample from GSR, as you can see in figure 1, collecting sample for GSR analysis is an essential step in the investigation process. Samples can be collected from a variety of surfaces, including clothing, parts of human body, specifically the hands, automobile, or the area surrounding the suspected firearm discharge. So the method of collection can significantly impact the results of the analysis. One common technique for sample collection is the tape lift off method. So through tape lift, we can collect GSR, which involves using a simple adhesive tape to lift GSR particles from the surface being analyzed. These samples are analyzed using the SEM for particle identification and elemental composition, as you can see in figure 1. The Phenom XL system is one of the most advanced tools for SEM and EDS analysis in the context of GSR testing, guys. So this system is a compact desktop SEM system that integrates multiple imaging functions into a user-friendly interface. So this system, guys, boasts the largest sample capacity of any desktop, so allowing up to 35 half-inch alumni stubs to be analyzed at once. So it uses a cerium hexaboride known by CEB6 solid-state electron source, which provides brighter and more stable imaging than traditional sources. And this one, guys, is well suited for automated SEM and EDS analysis, delivering high-resolution imaging with unparalleled stability. For analysis of GSR particles, Perception GSR is an automated software platform built onto the Phenom XL system. Perception GSR is here fully compliant with ASTM E1588, which provide a dedicated solution for GSR analysis. So the software here works by defining a scan area for each sample stub and then scanning it frame by frame. Using the backscattered electron detector, known by BST, it detects particles and determines their elemental composition using EDS. So here, the results are displayed in the form of a map showing the location of each detected particle within the scan area, as you can see in figure 2 here. Okay? Now, the perception software also offers users the ability to define scan areas, adjust the electron beam settings, and also customize the workflow to suit specific analytical goals. The auto video function allows users here to optimize brightness and contrast during the GSR run, ensuring the best possible quality image. So the dual thresholding feature helps maintaining accuracy by initially detecting particles at a lower threshold and then refining the detection at higher magnifications. So the core of perception software is its automatic feature analysis, known by AFA. I know there's a lot of abbreviation, but I think that you need to know these in the forensic ballistic field. So the AFA, which streamlines the detection process, helps the GSR particles to be detected, because the AFA displays both a micrograph and an EDS spectrum of the particle. So this feature allows investigators to confirm the presence of GSR and access additional details about the entire run. So the GSR reporter section helps researchers locate every particle detected during the scan for manual confirmation, which ensure the reliability of the results, as you can see in figure number 3 here. Okay? By the way, these are real photos. Now, in the control panel, the table groups particles by class and displays geometrical measurements for each particle. So the table of particle characteristics includes the micrograph and the field number that the particle was found in. Clicking on one will relocate the electron beam to scan the field again, and enabling users to perform EDS with a click and overlay a new spectrum with the spectrum obtained in the original run. As you can see in figure number 4, I'll open to you here, guys. Okay, so particles are marked as confirmed by saving the report, and a green check, as you can see, appears to indicate this fact. The report can be effortlessly like formatted. Okay, it can be formatted and customized to meet the needs of the forensic lab conducting the analysis. So the users here, guys, can annotate the data with comments, sample numbers, group descriptions, client names, and even project numbers in open text field, as you can see in figure number 5. Okay? And simply this is the SEM method. Now we're going to talk about, and finally we're going to talk about the comparison microscope. In forensic firearm analysis, guys, a comparison microscope is very essential tool for examining bullets and cartridge case. So this device allows forensic examiners to compare two samples side by side, looking for unique characteristics such as striations and cartridge case comparison. When talking about striations, guys, are the fine lines left on a bullet surface from the barrel rifling. These striations are unique to each barrel and can be used to match a bullet to a specific firearm. So in order to know if this bullet comes from this firearm, we can do the trial test and compare these two bullets. By comparing them under the comparison microscope and by matching striations under the comparison microscope, we can say if this bullet matched the specific firearm or not. Now, talking about the cartridge case comparison, it happens when the firing pin, breech block, ejector, and extractor mechanism leave unique marks on a cartridge case. These marks are invaluable for linking a specific firearm to a spent shell. I want you to know that the cartridge case mark is this one. This one, guys. Okay, can you see my drawing? And these are the striations. They are a very fine lines observed under the microscope. See, this is one bullet and this is the other one. And this is the line that separate two bullets under the microscope. Okay, by matching these lines, we can say if the bullet comes from a specific firearm, as you can see here. Okay. Now, in the case of shotguns, which lack rifling, the comparison microscope can still be useful for examining other distinctive characteristics, such as the gauge of the barrel and the presence of any markings on the shell. Lastly, guys, the restoration of serial numbers is really important here, because the restoration of serial numbers from any firearm is an important forensic process, even if serial numbers are scratched or ground off. Chemical etching techniques can often reveal the original markings, aiding in the identification of the firearm. So in conclusion, guys, each of these forensic techniques provides crucial insights into the ballistic properties of firearms, and the traces they leave behind help to solve crimes and bring justice to victims. And as we come to the class of Forensic Ballistics session, I'd like to thank everyone for joining and for active participation. It's been a true pleasure, guys, to delve into the complexities of forensic ballistic analysis. And I sincerely hope that the concepts shared will assist you in your future work. Many thanks also to the team of Forensic Fusion, particularly to Mr. Swapnil and Mr. Shakil for their seamless coordination. And I really look forward to engaging with you all again. And now I'll turn the session over to Mrs. Alaa Sheikh, who will discuss the criminological perspectives on behavioral disorder. Thank you.